Okay, hi everyone. This is a working session for our generalized physics project. Maybe we should call it generalized physics. I don't know. The the uh, the Ruliad and Rulial space is one of the kind of big ideas that's emerged from the physics project, and there are certain specific cases where we have been able to study the Rulial space and the I mean the story. Let's see, James perhaps has a way of describing. Okay, begin with a multi-computational system, i.e. a slice of the ruliad. Okay, so what we've got is a string replacement system with some initial condition, and it does what it does. And that's a specific rule. That's what you're describing as a single fiber. Is that right? Or something like that?
Well, we can just call it, for the terminology here, why don't we just call it a slice of the ruliad. It's a very modest slice. Later, we'll have larger slices.
Okay. Is it a slice or is it a path?
It's definitely not a path. I mean, it includes paths, includes several evaluation fronts.
I see what you're saying. I see, but it's a slice because it is all those things that are reachable by this particular rule.
Well, there are two rules, one initial condition.
Okay.
This rule goes on forever. So I guess it's a snapshot of a slice, I suppose, because in the full ruliad, the time step would be infinite, right? Mm-hmm. In the full thing.
All right. So now what's this?
Okay. Well, so the idea here is, so we've been floating this idea of observers performing some sort of equivalencing or coarse graining in order to extract, bulk, more aggregate properties from underlying Rulial behavior. This has been kind of in the lore of the Ruliad, yes, but we haven't made it functional. And it's not yet really functional, but at least in this notebook, we have some kind of visual models for beginning to acquire some intuition about this. Okay, so this is a very simple example. So I'm calling this a full Rulial domain. So a full Rulial domain is, okay, so here's one thing about observers that we were discussing. We've discussed it in a previous live streams, and Stephen, we've also discussed it, the two of us, which is observers should be able to perform some equivalencing, some coarse graining over a Rulial slice. Now, this involves some computational effort on the part of the observer, and observers are necessarily computationally bounded. So I think observers have what I'm calling a completion budget, which is, we have these Knuth-Bendix completions. That functionality has nicely been generated in the past. And what we can begin to do is we can take some Rulial slice and we can model, possible completions that an observer could take. And in this case, in this example that we have here, at least for this snapshot of this particular Rulial slice, we basically have all the completions. So this is a particular case in which the observer has a quite nice, expansive completion budget, and they're able to do what I would call two-machine computation over the entire slice. In other words, if we're thinking of the Ruliad as visually computing downward, the observer is able to compute kind of horizontally over these paths, lift one path from another and establish some equivalences between them. This is I'm calling this a full Rulial domain. There are other examples in which the completion budget isn't full and you're only able to exercise Rulial motion over part of this.
Okay, so hold on. The end result of this is the observer has conflated every, the observer, presumably, if you implement the green arrows,
yeah, right,
that will squash everything to a single path. Is that correct in this case?
Yes. Squash seems kind of, I'm not sure if squash is the right word, but yes, there's definitely, all the paths are going to be in some equivalence class.
But as far as the observer is concerned, the observer's conception, the observer's perception of what's going on is, in this case, is there's a single path.
I think so.
Because the observer had enough conflation budget, enough completion budget to be able to turn everything into a single path. So yes, let's have a more of an analogy of that. I mean, what is that like? That's like saying, well, let's see, what is that like? That's like, okay, you've got some, you know, I don't know. Let's think about this. You've got some weather pattern. It's got a whole bunch of clouds. They're all flapping around. The question is, do you successfully conflate those things into just saying it's a high pressure zone? That is, in other words, is you're at the level, I mean, in this case,
Yes.
the individuality of strings is being ignored by the observer. The observer is just smooshing together all of these strings that are related by completions.
Yes, and I'll point out that one reason why I think it's particularly easy in this case is that these two rules with this initial condition, I mean, it's multi-computationally reducible. If you know what step 9 looks like, you know what step 10 looks like. And so you're able to, I think, quite easily interpret this as some overall system that has some overall behavior. You're not going to be shredded or confused by the interacting behaviors of these individual evaluation fronts. And so that's a conjecture that I have, which is that it's much easier to perform these completions over any multi-computational system that is multi-computationally reducible.
Right. Well, I think that but I mean, this is the same statement as, okay, you think, this is the same thing. You think you're looking at a dog, but actually, in the actual evolution of the material of the dog causes it to turn into an elephant.
What?
And what's that?
What? I've never seen a dog like that.
No, I know, but that's the point. That's not the way physics works.
Okay.
I mean, in other words, it could be the case that the coarse graining that you have. No, for example, let's say you. Oh, I don't know. I mean, these are kind of silly examples, but I mean, the caterpillar turning into a butterfly type thing. You could take a what's a good example here? That's not a very good example. I'm trying to say that there's certain kinds of coarse graining that are successfully preserved by the dynamics of the world, by the actual sort of physics of the world. And there are other kinds of coarse graining that are not. This is the thing and the whole point is, one of the big points of the physics project is that the kinds of coarse graining that lead us to the descriptions of the world in terms of continuum space-time and so on,
right,
those are types of coarse grainings which are preserved by by the underlying dynamics of the world.
Yes, and they're accessible to the observer when they have some degree of coarse graining capability. They're not just getting distracted by the particular underlying rules and their individual evaluation fronts.
Well, so the statement would be, with a certain completion budget, as you're calling it, the observer can maintain successful conflation, to this rule-based, to this law-based, description of the world. It could be the case that in order to maintain, this is the Maxwell's demon type story. In order to maintain in order to maintain that simple narrative about the world, you would have to change your coarse graining procedure in an incredibly complicated way at every step. All right, but anyway, so this is a case where there's reducibility there. All right, why you call it? Go ahead.
Yeah, maybe I just had this thought that, belonging of observers to the same ontological region means that an observer can also be an observed object, right? So I think we're trying to extract essentially that there's a symmetry of relation between the observer and the observable, right? If A is, for example, I'm not sure how trivial that symmetry could be, but if we say if A is observed by B, then B should be observed by A. And this formula could be the necessary condition of equivalence of two different points of views, for example, that the observer can have, or how an observer does coarse graining.
So if I understand, Hatem, you mean the fact that humans, other observers, can interact, it necessarily implies that they have some shared rulial domain, so to speak. They're able to communicate meaningfully with one another, which is a non-trivial thing.
Yeah, I'm trying to answer what's the criteria of actually doing quiz screening for an observer, because is that what we're asking right now?
But see, the thing, one thing that confuses me is this.
Because I'm confused.
I mean, okay, between humans,
right.
We are presumably separated in Rulial space. We think of the universe in different computational terms. We operate slightly differently computationally, yet we can successfully translate from one set of human thoughts to another.
Sometimes.
Yeah.
Well, quite. And this is in fact, I was just writing about this in this thing I was writing right now.
Yeah.
About this idea about Rulial particles and the notion of robust concepts.
Right.
Because I think that is just like in space-time, there are certain kinds of things that can propagate across space-time without being, in some sense, shredded.
Yes.
And those things are the things we call particles, like electrons.
Yeah.
And similarly, between these different entities in Rulial space, there are certain kinds of things that are persistent. And I think those are essentially robust concepts. And so one question, but the thing that I find confusing here, and to Hatem's point, is it's one thing, between humans, we presumably, in some approximation, have this kind of, commutative relationship. If A observes B, B can observe A, and they can each have some understanding of what's going on in the other one. But it is much less clear when it comes to communicating with nature. That seems vastly less clear to me. I mean, in other words, us and the weather. We can look at the weather, but how is the weather looking at us? I mean, in other words, we simply don't know how to, we only know how to travel in Rulial space to other human minds. And we are making some vague effort in current times to be able to travel to computational minds, so to speak, computer minds, I should say. Not so much computational minds, computer minds. We have some vague anthropomorphization of, that's really the point, I suppose, is that our, well, yes, we have some perception that we know what's going on in the computer. And in terms of nature, if we anthropomorphize nature, we're saying we are at least projecting onto nature something which would be its, our view of its view of us.
Right. Well, this is why I think this notion of Rulial domains could be helpful. I mean, my kind of guess is that for humans, we have the same basic physiological cognitive faculties, though humans are going to differ in terms of what they pay attention to in their education, et cetera, et cetera. But ultimately, I'm guessing that the kind of domain that's accessible to humans is more or less the same. The budgets might differ, and the use of those budgets might differ. So this is why thinking about partial Rulial domains is also helpful. But I'm guessing that even for humans who, there's some Rulial translation that'll be required between them, the domain is more or less the same. But there's still some small Rulial distance that needs to be crossed because people are using their kind of budgets, to explore the Rulial domain that's available to them, in slightly different ways. As soon as we have completely different Rulial domains, like us and the weather, so to speak, then you have to consider Rulial motion between those domains, and that's in a section.
Okay, right. I mean, because my picture of how this works in the world is just like all us humans are crammed on this one planet in some random corner of physical space.
Yes.
All us humans are crammed in this one tiny box of Rulial space.
Yeah.
Out in the whole giant ruliad of possibilities, so to speak.
Yeah, that's right.
It's the same kind of story, and the question of what it looks like. Okay, so here's a question I've not really thought properly about. Okay, so physical space has this feature that has homogeneity. Right. That is, that the things that go on here on Earth are kind of the same as the things that go on elsewhere in physical space. We think about metamathematical space. So in that case, it's just a simple, the laws of physics work everywhere. Okay, that's a simple story. In metamathematical space, that story is considerably more complicated because that's saying we've got one piece of mathematical space that's algebra, one that's geometry, one that's, number theory, who knows what else. And what we're saying is, insofar as there's translation invariance, there's homogeneity there.
Yeah.
That is a non-trivial fact about mathematics that speaks to the existence of dualities between different fields of mathematics and so on.
Yes. Well, that's because in meta mathematics, rather than just having the universe do the work, we actually have to perform those completions ourselves, right? So the collective mathematical community is, it's like a crowdsourcing for the humanity's completion budget, right? We still have, I would say, in meta mathematical space, we still have a partial Rulial domain, and the goals of higher meta mathematics are to, lay the brick, so to speak, in these completions, trying to identify the connections that in principle are there, but we still haven't yet found.
Yeah. Okay. But so now let's look at the case of the ruliad and homogeneity in the ruliad. I mean, at some level, homogeneity in the ruliad is the story of the principle of computational equivalence. At some level, everything is, different parts of the ruliad work the same because of computational equivalence. But the question is there a higher level? I mean, computational equivalence is a deeply shredded equivalence. The question is there a higher level of equivalence? That's the
yes, there should be, definitely.
Well, okay, but what's the interpretation of that? I mean, that's a thing where, okay, so here's a very bizarre thought. Okay, we have certain thoughts about how human minds work. As we anthropomorphize the weather, we are applying those thoughts about how human minds work to the weather. In a sense, that's the same kind of thing as saying, let's take those thoughts about how algebra works and let's apply those to geometry.
Yes. Yes.
So in some sense, the concept of and then the question of whether, okay, so I mean, one issue is, in the case of physical space, we understand that our coarse graining has the effect of, we then believe in continuum space and things like this because of the coarse graining we're doing. In mathematics, in meta-mathematics, what we've understood is we believe in higher mathematics because of the coarse graining we're doing.
Yes.
And so what is the analog of that in full Rulial space?
Well, I like to think of it as just higher forms of computation. That's why I have this two machine,
which is what?
And
what,
machine concept.
Okay.
So it's instead.
Yeah,
well,
go ahead.
So the idea is, even in this case that we have here, you can take a multi-computation. It consists of individual evaluation fronts, and those individual evaluation fronts are just individual paths. In this case, once you start to form the completions, you're computing pathwise instead of pointwise. If we take the points to be individual states that are vertices, so now you're computing laterally, horizontally over those paths. And as you identify higher and higher equivalences, you're computing over higher and higher and higher paths.
Okay, let me see if I understand that. I mean, that's a very higher category theory kind of idea. I mean, what you're saying is, at the first level, you're doing an individual computation. Then you are doing a completed, conflated computation, which it is not self-evident. Okay, so what's not self-evident is that conflated computation is any easier than a computation that takes every, that just follows every path separately. And I think that's what you are talking about, multi-computational irreducibility, is the conflated computation, is it the case that the only way to do the conflated computation is to work out each path separately, or is there multi-computational reducibility,
right,
which allows you to make a statement about the conflated paths more easily than just following each path separately?
Exactly. That's the idea. That's why multi-computational reducibility versus irreducibility, I think, is very important.
Okay, so let's repeat that point for a second. Okay, so the point you're making is that successful coarse graining. Okay, so we can think of computational reducibility as being like a coarse graining in time. That is,
yes,
to say, it's the jump ahead possibility in
yes.
time. Okay, so what you're saying is multi-computational irreducibility is the kind of, in a sense, branchial or rulial transverse conflation.
Yes,
is the possibility of transverse conflation.
that's the idea.
And so then the question is, okay, so in the case where transverse conflation, I mean, in the universe, we expect that transverse conflation is hard, and only certain kinds of conflation are going to, I mean, what do we believe here? I mean, we believe that,
yes, I mean, that's why there's this idea of there being a budget, right? I mean, the idea is, on the one hand, in terms of the overall picture, if you're able to perform all this coarse graining, you get a somewhat simplified picture, but it involves more computational work, I believe.
well, wait a second. I mean, so the issue is, given a certain amount of compression, so to speak, a certain amount of conflation, I mean, what we believe is that in the end, there are slices of reducibility. Okay, so what we believe is that there are slices of computational reducibility. There are presumably also slices of multi-computational reducibility.
Sure.
And
literal slices of the Ruliad. Yeah.
Yes.
Yes.
Yes. So let me understand that. So you're saying that there are certain directions on which it is possible to do conflation and not have you follow each path individually, and which, so there are certain slices. I mean, just like what we've been saying about the possibility of the fact that there can be lawful physics, so to speak, as opposed to it's all just computational reducibility all the way down. Lawful physics is a consequence of the fact that we can exploit a slice of computational reducibility. And what you're saying is that there is also a sense in which, let's see, that we have identified. I mean, it's almost like we've identified a certain, in the normalization group, it would be like relevant and irrelevant operators. It's kind of like a direction in Rulial space on which we can, on which somehow some conflation is possible. I mean, is that what we're?
Yes, that's the idea, right? And then the point is that if you had an instance of irreducibility in the multi-computational sense, and what's interesting, it seems as though you can even have cases where you have individual rules that are reducible, but you put them into a multi-computational system, and the overall multi-computation becomes irreducible. We've seen some examples of this with multi-way Turing machines. As soon as you have multi-computational irreducibility, it becomes highly non-trivial computing, doing a two-machine computation, trying to compute horizontally over these paths, especially because this is running time-wise, and it's very much unclear when it's irreducible what's going to merge, what's going to branch, and what the overall behavior is going to be.
Okay, so hold on. I mean, first point you're making is that which is reducible on its own, like a single cellular automaton rule or something, when you mix it in with another one, they can both be reducible, but the whole is greater than the sum of the parts. Yeah. In other words, that you can make, I mean, as one's seen in many systems, although I think we have not studied this phenomenon as much as we might have done, the non-composability, so to speak, of or non-decomposability of computational reducibility. That is, or something that two reducible things can add up to something irreducible. Okay, but
it should be also that if you take enough irreducible computations and you put them together, you should get something reducible. Namely, something like we've seen these Turing machine groups for multi-way Turing machines. Basically, you take all of the Turing machines and put them together. But of course, there's some tape kind of restriction on those Turing machines. But ultimately, if you take enough of these rules and you put them together, you're going to get some sort of homogeneous space.
Well, okay, so that's an interesting claim. So that's some kind of coherence claim. But basically, if you do enough levels of completion in your classification of n machines, you're saying as n goes to infinity, you just have, it's like the infinity groupoid and things. You just have this blob that has in which you have in which there's some sort of necessary features of that. But
that's an interesting point, but that's actually not the point I was making. The point I was making was when we've seen cases where if you take, say, all of the rules, if you take enough rules of some particular kind, you take them multi-computationally so that all the states basically form some sort of complete graph. They form some sort of homogeneous space. Well, that homogeneous space is going to be multi-computationally reducible. But putting all those rules together, maybe if you start to remove individual rules from that homogeneous space, maybe some of those rules would be irreducible. But the point is, once you've gathered them all together, you eventually get something that is
right. So your point is that reducibility and irreducibility are neither what you get by combining them is different from what you get. That there just isn't any relationship. Composing those things together or combining those things together is, it's just like, if you have a chemical and you start adding random atoms to it, it can go from being poisonous to being not poisonous and back again.
Exactly.
Just by adding atoms, and it doesn't. It's not. Yeah.
Isn't that wild? Yeah.
Yes.
Yes.
Okay. So. Okay. Well, let's keep going here with what you're talking about. So.
Right. So we've been speaking, at least in this case, with this particular first example where we have all the completions. That's a very nice case. It's also kind of trivial to discuss Rulial motion for a full Rulial domain because you just have completion access to the whole thing, so to speak. But there are going to be cases, especially for some large slice of the Ruliad, where your completion budget doesn't extend over the whole thing. And that's where I think we see more of what you might think of as being Rulial motion. Once you have a full Rulial domain, you've been able, the way that I view it is, you've been able to effectively perform equivalency over the whole thing.
There's an analogy in space-time, right? The analogy in space-time is a space-like slice, and the equivalencing that you do is to say this is simultaneity, and we've got a certain moment in time, and all of space is equivalence together at that moment in time. All we care about is that it was 12 noon, so to speak. All of space is kind of equivalence together. But in reality, a typical actual observer does not equivalence all of space. You don't even see all of space. Right. Photons come in from little parts of space.
Right.
And there's a certain, perhaps, region of space that you have reasonably sort of become aware of, so to speak.
Yeah, exactly.
I don't quite understand this phenomenon of becoming aware of it, because that's what has to be happening. Is that what's the analog of completions in knitting together space? The answer is, to form a space-like slice, you are effectively, you can make an explicit construction in which you're sending and receiving photons and so on. You've got lots of little intersecting light cones, and that's kind of a way you can make the sort of truss structure that represents a space-like slice.
Truss structure, yes, right.
Right, because you've got crisscrossing, you've got crisscrossing photons, so to speak, forming that space-like slice, and knowing and being able to define what it means to be simultaneous across the space-like slice.
Yes.
So I think that's the operationalization of completion, so to speak, for I think it's almost quite literally that, okay, so here's a way to think about it. Okay, there is space, no photons involved, right? There's space, which in our models is complicated and has lots of things happening. But then, to implement completions for an observer, You add a bunch of photons. And somehow those are, I mean, just like your green thing here, what is actually doing the green thing? And in a sense, there is, in space-time in the typical view, and including in our models, because in our models it becomes even more explicit, space-time just is there. It's a thing. It exists.
Yeah.
Okay. And the construction of space-time into space-like slices and things like this, that is metadata on space-time. That is the if that makes sense. Space-time is there. It exists. It's already a thing.
Sure.
But now it is our exploration of space-time by this method of photons or whatever else that is, for us, knitting together. I mean, in other words, it's like the forest is there. There's nobody watching the trees, and one of them falls down. And similarly, in space-time, the fact that there can be a piece of space-time that's there, and until we actually go explore it with photons, it's like, who cares type thing.
But I think what's even stranger is that in the Ruliad, it has to be the case that not only are the purple edges there, but the green edges are there too.
Yes,
we're not creating them. It's more that we're able to sample them. You see, one thing that I was thinking about at the height of having COVID, when I was unable to sleep or what have you, is I was trying to understand, how do we actually make observers endogenous in these models? Because I don't like the idea that we have the Ruliad and then the observer is some sort of external, additional furniture in the theory, but it's not in the Ruliad. And I think that these kinds of models help, because the idea is that the Ruliad should include all possible rules, all possible initial conditions, and all possible higher order completions between them. And as soon as you have that, then simply taking subgraphs of the Ruliad, so to speak, taking slices, taking them as Rulial domains, this should provide a way to inherently model the observer. Because what the observer the observer is some sort of their particular,
subgraph.
Yes, I mean, we're basically,
we identify ourselves. We are proud of the part of our subgraph, so to speak. But in a sense, there's nothing different about our subgraph than any other part of the Ruliad. It's just like we have this belief in, that, I mean, okay, there's an analogy here. Okay, in a computer, right? There's data, there's metadata, but it's all bits in the end.
Right.
Yet, in a sense, there is, I mean, if I say, what's the right analogy? There's the content of my files, there's the file system, but it's all bits in the end.
Yes.
Yet, I'm identifying, how does this work?
Yeah,
I mean,
we get macros, basically.
Yeah.
Ultimately, we have a nice interface.
Yes,
and it's because we're probably sitting on top of like not a 2 machine or a 3 machine, but like a some very large number n machine. When we consider the fact that the underlying 1 machine or what have you is working over eames, we're quite large compared to eames. So we're probably actually performing quite a bit of completion, I imagine.
Right, but I mean, what you're doing is you're separating completion and computation, so to speak.
Well,
except you're not in the end, because you're saying in the end they're equivalent, which they have to be.
That's why I like this n machine concept. Is that the idea of the n machine is it just takes these notion of higher completions and also thinks of them as computations. They're just different kinds of computations.
Let's go back and understand that a little bit more carefully. Okay, so a Turing machine, a happy 1 machine.
Yes.
Okay. All right. How do we make a 2 machine out of Turing machines?
So you take a multi-way Turing machine, and especially when it's multi-computationally reducible, you start to compute over those paths. So imagine if you have something that's highly reducible, then you're able to move laterally.
Okay. So here's the immediate issue. Just a very structural issue.
Okay. Yeah.
Okay. Yeah. One thing that's awkward about Turing machines is that they are not, in a sense, structurally uniform. And that's one of the things that's great about hypergraphs, and Nick has even emphasized that even more about hypergraphs, is that to go from one Turing machine to another, it is a mess to do that with a Turing machine. You have to have a complicated encoding.
Right.
And one of the things that was, that we were doing in the mathematics project is to understand that, that one of the points there was rules about rules, so to speak.
Yes.
Yes. And that's where we're, in a sense, to make the end machine concept smooth, we have to be operating with something where you can have rules about rules type thing.
Yeah, that's a good point.
And I think that's a place where we should be, that is a piece of unification. This is, when are code and data the same? This is, in the case of mathematics, what we did was we went to a place where code and data are, we went to a representation where code and data are pretty manifestly the same. Theorems are operating on theorems type thing. And so I think the thing to think about is what is a good raw model of computation, and I think maybe we even had that. In the mathematics piece, we looked at string rules operating on string rules, which may be sufficient for what we need here, or maybe we have to go to hypergraphs. I'm not sure. But I think that's an important piece, is that it has to be true that the two machine is made of the same stuff as the one machine is made of.
I agree. That's important.
Right, and I think the string substitution system would actually be sufficient for that, because one is able to define rules freely then, right? Because you start with a given multi-way system, which one could see as a monoidal one category. One can then perform completions by introducing higher cells, and then you could just get to the infinity groupoid, right? In that case, maybe in machines could be better defined. But yeah, I have another thought actually I'm trying to see, because I'm a little bit confused here. So I think we're trying to say that information requires a context, right? But rather it's not a fundamental fixed context. It's rather a dynamical one. And it's the way we get this hierarchy of information. There is what we call a self-reference between information relative to a context and the structure of the context itself, because even the context itself does contain also information, like the ruliad, right? And depends on where you are located, you would also be let's say, how would you say that? You would be able to see certain things and not others, right? So there's also information that comes with the predefined structure, but that also shows that there is a hierarchy of information that one
so
has.
hold on, let me try and unpeel this.
Right.
So your information versus context is a little bit like the code versus data story.
Mm-hmm.
Your information is like data, your context is kind of like code, maybe. In other words, you're saying that
I think the context is rather bits in that case, right? Or not necessarily the code. Oh, well, the code is essentially bits as well.
No, but okay, so I'm missing something here. So you're saying that one of the features of the Ruliad, for example, is that it is an ultimate self-referential creature, because it is the it is self-reference to the self-reference to the self-reference until you reach the infinity groupoid type thing.
Right.
So trying to unpeel, you're saying you can decompose, you can cut that collection of self-references at some point, and at that point you have, you've ignored beyond the third level of self-reference, for example.
Let's say depends on how you coarse grain. Let's say the Ruliad, you would get a certain structure and not another, right? But that structure would be different than maybe some other observer trying a different coarse graining. He would get a different structure. But then you would also get this, depends on what kind of foliation you have, depends on what kind of coarse graining you do. You get these different levels of structures within that big structure, which is the ruliad itself. Not sure if that's
well, I'm
clear.
trying to understand what I mean. You're saying there are different kinds of coarse graining, and those reveal different aspects of the ruliad, which is surely true. I mean, the point, the big point that has sort of emerged in the last year or so is that this observers like us point. That is, that with certain sort of boundedness features or belief aspects to the observer, in a certain class of observers, there is a certain necessary conclusion of the coarse graining. If we go outside of that class of observers, sort of all bets are off. And I mean, I think that, well, so let's look for a second at, the two things that we believe are the essential features of observers like us: the belief in persistence in time and computational boundedness.
Mm-hmm.
And so, for example, I am just so hard pressed to understand what it would possibly be like to be an observer without a belief in persistence in time. Okay, the computational boundedness, I think it may be easier to understand what an observer is, what it would be like to be an observer without computational boundedness. I think that one, boy, that's so weird. Because, okay, I think that, our experience, our single thread of experience, we make decisions, we move on, those kinds of things. Those are, what's that?
No, I'm thinking ahead of what happens when you don't have to make decisions.
Yes, exactly.
Right? Yes.
Right. There are no decisions. You're not computationally bounded. There is, this is the thing that, this is the bizarre, actually, that's an interesting way to think about it. I mean, okay, so a claim is that, in the ruliad, our experience, we have any one of us has a fairly specific experience within the ruliad. We represent a particular, a particular sampling, a particular slice. As our technology and our minds expand, so to speak, so we represent a larger slice, a larger sampling of the ruliad.
But you know what's nice? This just occurs to me, which is, oh boy, you see, if you have, just a massive completion budget, you just do quantitative easing for your completion budget for indefinitely. Okay, so you don't have any budget. You're not computationally bounded. There's no need to even, oh, well, no, this is difficult. Here's the thing. Oh my God. One thing that's difficult is that we've kind of been supposing that you need some coarse graining because you're computationally bounded.
Yep.
But coarse graining does require some additional kind of computation. You see, what I'm trying to understand is, if we were completely computationally unbounded, would we see the world through completions, or would we just see the raw underlying
that's a good question.
computation?
That's a good question. I mean, basically, what you're saying is you could use up, I think it's like time dilation. You can use up, what is time dilation? Time dilation, and it may be exactly the same phenomenon as time dilation. Okay. So, you have a certain computation budget. You can use it to figure out how you evolve at a particular place in space through time, or you can be recreating yourself at different places in space.
Yes.
And then most of your computation budget is used in motion, not in evolution.
Right.
Okay, so here it's the same type of thing. You can either decide to conflate things together, or you can decide to figure out how things evolve in the success, as the threads successively evolve.
That sounds right. Yeah.
So okay, so let's walk back through this for a second.
Yeah.
Okay, so let's talk about time dilation, the ultimate time dilation, so to speak. Okay, so that is saying the ultimate time dilation is effectively between Rulial motion and evolution through time. Okay, so time dilation of Rulial motion must have to do with you either keep on, I think we thought about this before, you either keep on kind of somewhere you're trying to reach out to somewhere else in the ruliad. Okay. And you can do that by having essentially an interpreter translation going on, a computational translation going on between what's happening at a different place in the ruliad and what's happening for you. Like in your pictures here, we could be thinking of the green things as being essentially translators. They're transducers from one set of strings to another set of strings.
Sure.
Okay, so then you can either go off and green yourself, so to speak, and you can go green for a while, and then you can, and then you go purple, so to speak, and you can either try and pull everything back to a single purple point, single place in, a single purple line. You're pulling everything back by essentially, let me think about this. How does this work? So what we're saying is you're either, it's something like you're either going to use your budget to, okay.
Yeah.
Here's a way to think about it. Okay. Somebody is telling you about category theory, and all you know is about algebraic topology, let's say. You don't understand any of the category theory stuff. Or let's not take category theory. Let's take foo theory.
Too meta. Yeah, okay.
Yeah. Let's take foo theory. Foo, F-O-O theory.
Okay.
Foo theory, which is some kind of, different theory from category theory. Okay. Maybe we could take an example. Let's take Turing machines and combinators. Yeah, actually, that's a good example. Let's take post rewrite systems and combinators. Okay. So now you know about post rewrite systems. You're happy. You're thinking in terms of post rewrite systems. You understand string rewriting, et cetera, et cetera, et cetera. Somebody then tells you, look at these combinators over here. Okay. So one strategy that you can adopt is every time somebody says S of S of K of K of K, whatever, you translate that into your string rewrite systems.
Right.
Then you understand it there.
Right.
And then you translate it back and you say, well, actually, that means K of whatever it is does this.
Yes.
Okay, that's one strategy. The other strategy is to sort of, well, again, let's think about this for a second.
Yeah, it's like in this case, just to think about it categorically for a second, it's like you're taking kind of the action of the functor, and then you're seeing what the morphism is on the other side and on the string rewriting side. Or you could allow the things to run, and then you could take the functor across after you've already run them, so to speak. Yeah, it's something like that.
Yeah, right. It's that kind of thing. But so now the question is, so I think this translation, I think that what you're talking about between sort of the completion budget versus the sort of the evolution and so on, I bet there's the analog of Lorentz invariance. There's a Lorentz transformation, which says it doesn't really matter. You can either choose to think about things directly in terms of combinators, or you can keep on doing these translations. Both work, but if you keep on doing the translations, you're going to make less progress, because if you can think directly in combinators, you can swing from from tree to tree, so to speak, directly there, as opposed to, oh, wait a minute, I got to do the translation back and then keep going that way. So in other words, what you're saying is there is the invariant interval, so to speak, is somehow the same. The computational budget is somehow the same, but you can choose to use it in different ways.
But you see, I think that there's one caveat, which is I think when the multi-computation is irreducible, I think you have to let the thing run. You have to let it evaluate before you can start to do the completions. Otherwise, I don't see how you do it the other way around.
Okay, so hold on. So the issue is, right, because of in multi-computational irreducibility is a transversal irreducibility, so to speak.
Yes.
And what we're saying is, okay, so let's turn this back for a second. I mean, so I think this relates to Lorentz transformations on thermodynamics, which is a big mess. That is, you have the question of, you've got this computationally irreducible process happening in time. And the question is, what can you do? So I think this is a little bit muddled, but I think, it's always been an issue. What is the Lorentz transformation of a temperature? What's the boost of a temperature?
Okay.
It's a mess.
Right. Yeah.
And it's one thing. It's all well and good if you say, I've got this well-organized material object, and I make it go faster, and I can do all the usual relativity reasoning about it. Now, I think there's something that goes wrong, and I bet it's going wrong for the same reason. I bet that there's a failure to be able to make that Lorentz transformations somehow are things that can happen, that somehow there's a relationship between reducibility and the possibility of a sort of coherent Lorentz transformation.
Yeah, I get it. That's interesting.
I can't quite join those dots, but I think that what's being said is this trade-off, to make the trade-off between that basically for second law type reasons, you cannot make a trade-off between something that is sort of heat based and something that is mechanical work based. That in some sense, that like in your pictures here, you can make, when it's reducible on both sides, like mechanical work everywhere, then you can make the trade-off.
Yes, when you could say, I mean, to take this image where we are right now, you could basically say, just compute horizontally as far as you can, and then just run it all the way down. You could kind of pre-commit to the kind of two-machine translation. You do that, you do the functor part first, and then you just evaluate the whole thing. That's not going to work for anything that's multi-computationally irreducible.
Okay, but so let's look at the question for, I mean, the claim is Lorentz transformations are creatures of mechanical work and not creatures of heat.
Okay.
And to say that we're saying the trade-off between, I have this feeling, I've sort of vaguely probed this question about Lorentz transformations of temperature for years. And I know it was a question in the very early days of relativity. People were pretty confused about it. And I wouldn't be totally surprised if it isn't one of those things that has been sort of hanging out for 100 years as a little loose end, so to speak, that actually is the beginning of a thread that you can pull that turns into something much bigger. In other words, it's quite unclear what, I mean, so you have, I have to think about this. I mean, all the standard mathematical techniques, and I mean, the thought experiments, an interesting question would be, a rather elementary question perhaps, would be to take the thought experiments that give you relativity and say, what happens if you have heat in that picture? Okay. So, I mean, the thought experiments that give you relativity are all things about, a light pulse goes here and you get a light cone and all that kind of thing. By the time there's heat, by the time there's computational irreducibility in that picture, it is much less clear to me, at least, what's going on.
This seems like a good application. I mean, we might not get to the bottom of it today, but this is something we should definitely pursue. This is a good idea.
Yeah, right. But okay, but so let's come back to, I mean, I think the bigger picture that's emerging is this trade-off between, space and time, completions and computation, coarse graining and computation, so to speak, insofar as completions and coarse graining are the same kind of idea. These are all sort of, they're all trade-offs. I mean, you can take, well, okay, and this whole question about belief of persistence in time, maybe there's an additional piece here. Maybe there's something else that is needed for observers like us. Maybe there is some sort of localization to a certain number of degrees of freedom that has to be there. In other words, we believe we're persistent in time, but we also believe, well, it's basically the computational boundedness statement. We believe that we are bounded with respect to the ruliad. We occupy just a small part of the ruliad, and we believe that we are, yes, essentially what it's saying is we are like rays in the Ruliad. We have a persistence in time, but we also are of bounded extent in the Ruliad.
Right. Well, the question is, does persistence, so let's say, I mean, whatever n level we are for the n machine, whatever kind of degree of coarse graining or completions that we're performing, does persistence in time mean that as we're moving along in our particular slice in the Ruliad, that completions on that order can constantly be maintained? That is, whatever, how should I put it? Whatever, it's not in infinity groupoid, but whatever kind of structure that we have, we're able to kind of push that through the Ruliad without it being broken up. Because imagine all of a sudden you reach some obstruction and you were doing, 32 levels of coarse graining, and all of a sudden that thing gets ripped apart and you can only do
Sure.
3.
I think that can happen. Right. I mean, that's a big question for, that is our continued existence. And it's the same kind of thing in space-time. You do just fine, believing that you're persistent in time and believing that there's pure motion. You're a teacup or something, and you remain a teacup in most places in space. But if you get near to a space-time singularity, you're not really a teacup anymore.
Right.
It's hard to maintain that structure. And I think similarly, there are presumably, and that's a good question, to what extent there are singularities in Rulial space and what that's like. And what would it mean to have an infinite curvature singularity in Rulial space? In other words, that's a thing, that's a place. Well, let's see. I mean, there's some things like space-like singularities where time ends. I'm not quite sure. I mean but I take your point that the observer who believes that they're this lump of stuff in Rulial space.
There you go.
If the observer is shredded by coming too close to a Rulial singularity, what does that feel like? Let me think about that for a second. I mean, zoomed out to the level of sort of cognitive, you have a certain point of view about how things work. You have a certain paradigm. And let's see. I think what it means is that no paradigm works. That is, a singularity, a Rulial singularity, is a place where no coherent paradigm works. That is where it is impossible to reduce what goes on to something which can have a narrative that exists for a computationally bounded observer, blah, blah, blah. In other words, there's a, in the absurd thing that people sometimes say, you are not expected to understand this. It's the ultimate, you are not expected to understand this point, because nothing can, quotes, understand it. But I think coming back to this question about sort of existence in the Ruliad and this idea that, it might seem lame that we represent sort of small lumps in the Ruliad. But I think this point about what would it be like to be bigger in the Ruliad, I think what it is like, if you are not successfully able to complete things to the point where you have a single thread of experience, because that's what we're saying. If we're not completing things to the point where we have a single thread of experience, which is our typical human experience, then that is the case where we can follow multi-computationally, we can follow multiple threads, et cetera, et cetera, et cetera. This is my kind of, imagine what it would be like for us as humans to not have that single thread of experience. I mean, this is the kind of the multi-way trance type idea. What is it? What would it feel like as a human to have, multiple threads of experience running at the same time? Now, an interesting question is, if you have a group of humans together, they are like multiple threads of experience running at the same time. But notice the important point that the level of communication they have is very small.
Yes. Yes.
Right? I mean, they're just exchanging Rulial particles, so to speak, of words and talking to each other and so on, which is a very minor. That it's not like they are deeply interwoven. They're just, their thoughts are not deeply interwoven at the level of individual neuron firings. They're just, bouncing big words to each other, so to speak.
Yeah, it's funny though, because if I imagine if I had 10, POV views of 10 different people's lives, and they were all superimposed over one another. That seems totally incomprehensible, right? If I was an entire startup worth of people or something, right, and I had all of their experiences at once, that sounds quite difficult. But on the other hand, I mean, I'm a human body. There are many organs that are feeding into my brain, and I'm able to kind of manage all of that. So perhaps if I had some different cognitive ability, it wouldn't be that difficult to,
I don't agree.
be
I think it's
people.
a fundamental feature of consciousness, and so the human condition, that we have the single thread of experience. I think that in bizarre neurological kinds of situations where that isn't true anymore, I think it's really hard to maintain kind of a human-like.
Not human-like. Some other form of, if you had some different architecture.
Right, but which we find very hard to understand.
Exactly.
And that's
yes.
But the point is that as we, if we're all uploaded consciousnesses, and somebody says, "Wait a minute, what do you mean you're running as you only got one core in your CPU? Let me upgrade you all, so to speak." Right? In other words, you're
yeah, I get it.
Okay, yeah. Then what on earth happens? Because I think in the end that that's kind of this is the claim that that's the end of existence, so to speak. That as soon as you have upgraded to the point where you are deeply multi-threaded and you are occupying more and more of the ruliad, then you basically don't exist. That, in other words, that the concept of existence as we experience it, so to speak, depends on this idea of sort of single threads of experience through time. And that as soon as you allow yourself to be kind of extended in Rulial space and to have multiple threads and so on, that, that's a question. In the end, so the concept would be that our notion of existence has to do with the fact that we can successfully pull things in through completions so that we are single-threaded, so to speak.
I know, but imagine, what if it's possible, again, with some other architecture, that you could take what are basically individual threads of experience and find some meaningful completion over those? Would not be surprised.
So what you're saying is, imagine that.
It's like, what's it like to be a species? What's it like to be, we have no idea. We're too
right. So the claim would be, who speaks for the species, so to speak. That is, you've got the whole species doing all these different things. In the case of our brains, who speaks for those 100 billion neurons? Answer: we go yak yak yak, and we have a single thread of speech for that on behalf of those 100 billion neurons.
Exactly.
But one question you might ask is, given a species, for example, what is the coherent communication of that species? Just like we have this way of taking all those 100 billion neurons in our brains and forming a coherent stream of communication, of differing degrees of coherence, some kind of, is there a way, can one speak for a species, so to speak? In other words, because it could be the case, and that's a good analogy, it could be the case that there is no kind of coherent thing that you can say, or it could be that there is a form of completion where that allows you to coarse grain across the species and have something coherent to say.
Right. Well, I'm guessing this is what religions have basically tried to do. This is maybe what the deities are. They're these kinds of, you take all the species and you try and usually anthropomorphize it into some individual, that speaks
Well,
for
I mean, that's
something
an
that you have in
animism.
common.
That's an animism idea, I think.
Sure.
Maybe Hatem has something wise to say about this.
Yes.
I'm not sure if I have anything wise to say about this, but very interesting indeed.
I mean,
this has gone somewhat philosophical. I did want to show some other pictures that I had here. I don't know how much time we have.
we're kind of running out of time here.
Well, let me just show you. I wanted to show you the last picture. I wanted to look at motion between full Rulial domains. Okay, there are two kinds of setups that I can imagine here. So yeah. I mean, so you can imagine having two domains. They're either disjoint or they're not. In this case, these are two isomorphic but nonetheless distinct rules. And I did a very easy example where
A's and B's and C's and D's. I see it.
Yeah. Yes, right.
Okay.
Now, there's another example where you have some Rulial slice. So let's say you have some Rulial slice that happens to be causally invariant. You can imagine that there are other rules that could be added, or there's just another set of rules that would also still be causally invariant. And so in that example, the Rulial motion is, let's say you have some Rulial domain, but that's actually some subpatch within some larger Rulial slice. Then you could do Rulial motion, within some larger full Rulial domain that's still invariant. In this case, they're disjoint, but you're still able to undergo some motion from one to the other. Now, I was able to visualize these. I'm really not sure, though, what it would mean. What would it mean? So let's say you have, I can see this appearing in things like metamathematics, for instance. So let's say you have rules. They have some structural similarity between them, but in terms of, say, the syntax, they're just totally different things. What is that? What is Rulial motion between these different? It could be in mathematics. It could be a fabric or a cone.
But that's what concepts are. That's the concept. The concept of a robust concept.
Yes.
That it transcends the details of its syntax, so to speak.
Good. Well, good. So this is an initial attempt to visualize maybe what a concept is. Then, maybe.
Yeah. Because in a sense, the ability to form concepts is essentially the essence of abstraction.
Yes. Right.
And so, the question of this sort of isomorphism between, in a sense, the presence of functors.
Mm-hmm.
Okay, the
square root of a stanza.
Yes, right. The existence of a functor is somehow, well, the question is what survives across, and what are the robust things that survive, even as you are kind of converting the syntax, even as you're dramatically converting the syntax.
Yes.
What kind of a thing survives as you convert the syntax?
Well, the idea in this case, so I have these dotted lines, but the point of what the idea should communicate is the following. If you look at the top of these, well, not quite the top, but if you go down to the second tier for both of these multi-computations, you can see that there are these green double edges, these green loops. The point is, if you look, you can basically transport that first green top loop across to its corresponding blue one. Mm-hmm. So what you have is you're transporting these equivalences across Rulial space.
Yeah, I get it. Right.
So it's not that that's why you're able to kind of lift something, because it's not that the individual states that that you're really trying to extract and move. It's that you found some coarse grain, you found some equivalence that is present in the other structure, and you're able to move back and forth between them.
See, one of the things that I think is sort of an interesting perspective on all of this is the limit of technology is a limit of being able to make as many translations to be as big as you can be in Rulial space. That's kind of the, to have as much motion as possible in Rulial space.
Well, what's cool about technology is we're able to augment our reach in Rulial space without having to accept the consequences of what it would be if we ourselves kind of physiologically as observers actually had that reach, which I think is
I don't think that's a surviving story. I mean, isn't that well, think neural implants. I mean, it's not.
Well, okay, but yes, okay, maybe we will. That's true. That's true. We are pushing our that's a good point. But for some extent, I mean, yes, that's a good point. But the point is that we can still do that gradually with trials and consciously. The point is that
I know.
We have this extended, we have this, prosthetic technological kind of extensions of ourselves, but we don't have to.
Look, I think there comes a time when when the human single thread is irrelevant, and that's the time when, and in a sense, the bizarre thing is that the thing that we are seeking in technology is to essentially extend our reach in Rulial space. And I think, I'm increasingly realizing this is a be careful what you wish for type of situation, because in a sense, by as we generalize humanity, so to speak, eventually we have nothing. In other words, as we generalize to the point where we are, I mean, it really comes. What's that? Yeah,
I get it. But I think the point is, though, I think one other lesson from this study of motion in Rulial space is that I think enlarging your reach in Rulial space works if you have a thesis, so to speak. That is, if you're able to gain abstraction in Rulial space. I mean, that's basically being, you have some kind of architectural progress in Rulial space. If you're just getting larger and you're getting shredded and you're becoming overcome by all of the different Rulial possibilities, that's not a good way to grow in Rulial space. You have to grow kind of upward along the abstraction, upward in the abstraction tower.
Yeah. Well,
if you try and reach outward, you're going to be over.
This is the question of colonization in Rulial space. What is the
Yeah, you have to do it with skyscrapers, basically. If you try and if you try and become the Rome of Rulial space, you will collapse.
Interesting claim. I mean, the remaining issue, and one that I've been, is what about ruliology? What about because in Rulial space, unlike in physical space, if you want to get from here to there, you have to have a rocket that pushes you, so to speak. Yes. But in Rulial space, we can write down a rule because of the equivalence between computation and reality, so to speak. We can just write down a rule which, immediately transports us to some random place in Rulial space.
Yes, exactly.
And the problem is that thing that we get to at that random place in Rulial space has no connection to us. It's just, this. But the thing, the only thing that it has connection to is the homogeneity that comes from computational equivalence.
What do you mean by no connection to us, though?
Well, I mean that it's like the weather. It's like a random cellular automaton. It's like how do we,
But what if we had some sort of map of the ruliad? I don't know exactly how this would work, but it would be, the point is that let's say you do ruliology and you find some very nice creature. You have no coordinate for the creature. You have no idea really where you've gone. You've kind of closed your eyes and you've ran in some direction and then you really don't know where you've gone. But is there some meticulous way to leave breadcrumbs as we're doing ruliology so that we have some way to coordinatize it?
I don't know. I mean, that I think has to do with the story of completions. I mean, if you just say, I'm going to pick the bits for a rule at random, that's one thing. But the other possibility is I reach that rule by actual motion, by some completion type actual motion. Mm-hmm. And as opposed to just the jump through hyperspace, so to speak. I mean, where you just land there. If you've reached it, and that's the same thing that you were referring to in the case of, the neural implant, humans dissipate in the ruliad type thing. The claim is if it's gradual, it makes more sense than if it's a jump.
That's the idea. That's the idea. Yeah.
I think it's the same thing as you imagine jumping around in history, so to speak. If you are, I don't know, it's a certain, I mean, it's the same sort of story of is there a continuity of understanding between an archaeological remain and the present day and so on. We need to wrap up because I have to go back to some
Something
to the
totally
day
different.
job, which is very different, and it is a very what can I say? It's a different place in Rulial space. So
Yeah.
Hatem, I'm curious if you have any comments, sort of philosophically.
Yes, just final comments. Just maybe a comment about what James said. What if we have maps about the whole ruliad, which in fact actually each observer has kind of a low resolution map. This is how kind of how we function, and this is sort how you can function as long as everything's going fine. Like sequential things happen sequentially. You have you're being consistent along all of that. You don't have to adjust your map. It's only when things aren't going the way you think you might be going, or you think they might be going, and then you have to adjust that map. So I think, yeah, we all have kind of a low resolution map of the whole ruliad. Each observer does. But okay, so anyways, speaking of the motion in the ruliad or rulial motion, I think these are concepts indeed. And just going back to the religion question, I think one can think of religion as being a meta heuristic that simplifies, let's say, equations to all people, right? And that's why it's kind of it's kind of being around for so long. It did outlast time for so long because it was able to communicate or to represent a concept or an idea to kind of all observers based on all locations. Of course, each observer has kind of come up with their own religion, because based on where they are located in the ruliad, we have so many religions for one God, right? It kind of makes sense, but the concept itself, the concept of religion, one could think of that as motion or concepts in general, for sure.
Well, I mean, your point is that, I mean, any kind of cultural, whether it's a single language, whether it's a single culture, whether it's a single belief system, so to speak. Right. Your point is that, in a sense, is a way of conflating lots of separate minds. Is that your point?
More or less. You have the concept, but how people see it would still be from their subjective setting or from where they are located in the ruliad. Thus, they would come up with their own religion to describe that concept, which is essentially the same concept for all observers, but it's the case that observers are located in different places so that they would see it in different ways.
Yeah, right. It's like, everybody's looking at the same monument, but they're not in the same place, so the monument looks different to them. I mean, even though it's the same monument, so to speak, in some sense.
Now, one last provocation, which is one reason why I introduced this idea of partial rulial domains, is just to respond to Hatem. I wouldn't presume that observers have a coarse-grained view of the whole ruliad. See, my kind of understanding is you have the whole ruliad, and then you're going to have basically subgraphs, and those subgraphs can correspond to higher end machines where you have completions and completions and completions. But I presume that whatever observers observe, it happens to be whatever kind of sub-patch of the ruliad or even some particular rulial slice that they're able to effectively coarse grain. I think that coarse graining the entire ruliad, it sounds very expensive.
Yeah, I would think that mostly we exist just like we exist in small places in physical space, so similarly in the ruliad. Anyway, this is to be continued because we need to go off to other things. But this is a lot of very interesting things to discuss, and I look forward to doing so again quite soon. And
I'll think about this Lorentz.
Yes, I think there's something
question. That's a good thread to consider.
Okay. All right. Thank you all, and thanks to folks on